as we've been talking about centroids, I want to talk about a kind of related topic that you're going to see more as you go through your schooling, and especially if you go through a fluid mechanics class, you're going to see this come up. But this is a kind of basic introduction to this idea of fluids and pressure in. So whenever you go underwater, you can feel the pressure of the water on your body. And we know that the deeper you go, the more pressure you feel, right? If you check your watches, you'll often see that they're rated for a depth rating, right? It'll say waterproof up to 20 meters, waterproof up to 50 meters. And why do they have these ratings? It's really because of the pressure that the watches can withstand without breaking. Because as you go deeper into the water, there is more pressure on you. And Pascal's law states that a fluid at rest is going to have equal pressure in all directions, but that pressure increases with depth. So what that looks like in practice is when you have some body of water, and let's say we have a boat. Here's the side of our boat. The pressure acts like a distributed load, a triangular distributed load on the side of that boat, where the pressure gets greater and greater the deeper you go. So as we're talking about these, I want to introduce to you this idea of how we find the pressure on the side of our boat here, right? And we do this with this equation here, that our pressure, that's what this P is here, our pressure can be given to us by the density times our gravity times Z, which is depth. Depth specifically is depth below the top of the fluid. So the top of the fluid is our datum, right? It's our 0 point, and then our Z is measured below the top of the fluid. So our top of fluid. And this equation we can also see is rewritten here with this gamma. And gamma in this situation is specific weight. And specific weight is literally just density times gravity. That's all specific weight is. We use it because we're here on Earth, so specific weights are different in places. But on Earth, the specific weight of water, our gamma for water, specific weight of water, is 62.4 pounds per foot cubed in our unit system, and 9810 newtons per meter cubed in metric. So these numbers are important. You'll want to keep those somewhere so that you know this for fluid pressure, because we typically work with water. We're typically talking about underwater scenarios. But you might use different specific weights for other fluids if you're ever in those situations. But let's go ahead and work through one example just to kind of get a feel of how these pressures work, which again is going to be very similar to our distributed load, where we can find the loading on the side of the boat as a resultant force. This example asks us to determine the magnitude and location of the resultant hydrostatic force. Ooh, statics and hydro, right? It's hydrostatic force. Hydrostatic force acting on this submerged plate, this little guy in yellow that I have here, plate AB. So what we're going to do is we're going to find the pressure that's acting on the plate and turn this into a distributed load, and then we can use what we know about distributed loads to solve what the pressure is, the resultant force is on this plate. Right? The water is causing a force just by existing. And that's our distributed load. That triangular distributed load that we had seen before. But now we're just interested in how it's impacting this area AB. Right, so just cutting this slice out of our triangle of our distributed load. So the first thing we'll do is we'll use that pressure equation to go ahead and find what the pressure is at A and the pressure is at B, so we can look at just this slice. So those pressure equations, pressure equals specific weight times our depth. So we can do these for our points A and B. So at A, notice our specific gravity is going to be the same because our specific gravity is always of the fluid itself, so of the water, which is going to be, in this case we're dealing with metric, so 9810 newtons per meter cubed times the depth, and our depth at A is 2 meters below the surface. And so that's going to give us a pressure of 19,620 newtons per meter squared, which a newton per meter squared, you might also see this listed as a Pascal with a symbol PA. That's Pascal, and all it is a newton per meter squared that is named after a scientist as a unit of pressure. So pascals and newtons per meter squared are the same thing. Then the pressure at B, same deal, same gamma. 9810 newtons per meter cubed times the depth at B, and the depth at B is 5 meters below the water's surface, right? That 2 plus 3, so 5 meters gives 49,050 newtons per meter squared, or pascals. Alright, so we've got those, but the problem is that we're used to seeing these distributed loads in newtons per meter, right? In a force per distance. But we don't have that here. So what we're going to have to do is, they do give us a width, right? So we need to multiply our width by each of these pressures so that we can get just the loading, right? So it's turning this into a force over an area to just a force over a. So we can get W by multiplying our pressure times the width here, right? This width they give us of 1.5, which maybe not W is the thing to call it. Maybe we call it B, I guess. Lowercase b. So my load at A is going to be that 19620 times 1.5, which will give me, I'll simplify this a little bit, 29.4 kilonewtons. And at B, I have 49,050, again times 1.5, same width across this whole plate AB. Multiply that, I get 73.6 kilonewtons. So now I have something that I've seen before, right? I have something that I can work with. If I go ahead and draw get rid of this math that's in the way. Right, I've seen this before, where I have a distributed load. This is on my plate AB here. And now I know that this end is 29.4 and this end is 73.6 kilonewtons. Oh, sorry, these should be kilonewtons per meter. They are loads, kilonewtons per meter. So I can now use what I know about distributed loads and separate these into their shapes to find that resultant force and that distance. Oops. So let's do that. Right, so I can separate these out, and I know that I'll have, right, this triangle that has this height of whatever 29.4 minus 73.6 is. What is that, like, or not 30, 40, 43.2, something like that. 44.2, somewhere around there. And then my other shape here with a height of 29.4, and they both span this distance AB of 3 meters. So again, it's that idea of separating them out into their shapes and then finding their centroids, right? So for this shape, my centroid goes through the halfway through the center here. For my triangle, it goes a third of the way up from the bottom. And so I can do my resultant force is going to be that 29.4 times 3, right? Just the area of that shape, plus the area of my other shape, 1/2 base times height. 1/2 44 times its base is 3. So I get a resultant force of 154.5 kilonewtons. So that's the magnitude of my resultant force. Again, this fluid pressure is no different from any other distributed load. It's just a matter of understanding how this triangle functions in the water. And the last part was finding where exactly this hits, which we do with a moment. Right, we can find this distance. I'll go ahead and take a moment about our B point here. So if I take a moment about B, I'm going to have that my 154.5 times whatever the height of that final resultant force is equals 29.4 times 3 times this hits at 1.5 plus 1, this distance here is 1, times 1/2 times base is 3 times height is 43.2. Right, so just taking a moment equation to find what that resultant height is, what that height above B is. So that gives me a height of 1.29 meters above point B. And that's it. We've done this before in our equivalent forces and our distributed load chapters. It's just bringing this all together into one thing with our centroid conversations to apply to this new idea of pressure, which again, you're going to see a lot more in your fluid mechanics class. This is just kind of a soft intro into what you're going to be seeing in some of your future classes.